Hi, today let's see how we can delete alternate nodes in a linked list. Suppose we have this linked list, say 1, 2, 3, 4, 5, 6, and null, and they are following one based indexing. So 1, 2, 3, 4, 5, 6. Our task is to delete all alternate nodes, which means nodes at even positions like second position, fourth position, and sixth position, and so on. So the output would be like 1, 3, 5, and null. The thing to understand is we are not deleting by value, we are deleting by position. So every time we keep one node, we remove the next one. So now let's look into the iterative approach. So let's say we have the same linked list 1, 2, 3, 4, 5, 6, and null. Here we use two pointers. Say one is prev and another one is node. So prev points to the current node and node points to the node that should be deleted. Okay, so ideally for 1, 2, and 3 in this position, prev should be at 1 and node should be at node 2. So this should give the output as 1 and 3 because 2 will be deleted. So by deletion, I mean we delete the alternate node by just skipping it. So what happens is prev dot next is node dot next. This way we are deleting 2 and 1 will be pointing at the third node. It becomes like 1, 3, 4, 5, 6, and null. Now prev moves to the next valid node and node moves to the next alternate node. So prev will be here and node will be here. We repeat the same step. Prev dot next equals to node dot next. 4 will be removed. It becomes 1, 3, 5, 6, null. Prev will be moving here and node will be moving here. Again, prev dot next equals node dot next. This will be deleted. So it becomes 1, 3, 5, and null. So this is the final output. We repeat the entire process until we reach the end of the list. Since we reach the end of the list here, we stop the process. So the time complexity of this approach is big O of n because we are traversing only once, and big O of 1 will be the space complexity as we just use the pointers. Now let's look at the coding part for the iterative approach. Alright, let's code up the iterative method. We are given the head of a singly linked list. Our job is to delete all nodes at even positions and modify the list in place. For the base case check, we should see if the list is empty or not. There is nothing to delete obviously, so we simply return. If not head, we simply return. Now let us initialize the pointers. We will use two pointers. Prev pointer to point to the current valid node and node pointer to point to the next node, which is the alternate node that is to be deleted. Therefore, prev is head and node is head dot next. Our scenario is like we continue as long as both pointers exist because we need to delete a node. Therefore, while prev and node exist is the condition. Okay, now to delete the alternate node, we simply skip it by changing the next pointer, that is prev dot next is node dot next. This particular step removes the node from the linked list, and after deletion we move the node to the next alternate node. Therefore node is prev dot next. All right, if node exists, we move prev to this node and update node again, and therefore this actually maintains the alternating pattern as well. And now if node prev is node and node is node dot next, the list is modified in place, so we don't need to return anything. And once the loop finishes, all alternate nodes are deleted as well. So let's go and run the code. As you can see, for the first input linked list, we have this linked list, and we removed the alternate even nodes. That is 2 is removed, 4 is removed, and 6 is removed. So this is the output linked list. And similarly, we have an input linked list, say 99, 59, 42, and 20. We remove 59 and 20, and we are left with 99, 42, and null. And for this case where we have only one, we just simply return because there is nothing to delete here. we simply return 10 and null. Now let's look at the recursive case. All right, let's quickly look into the recursive approach as well. Let's say we have this linked list A, B, C, D, and null, and head is pointing to the first node. The recursive approach follows the same logic, but it is just expressed recursively. So the final linked list should be A, C, D. At each recursive call, we delete, this is the first step, we delete head.next, and then we call function on head.next.next. So the flow is more like delete alt of A to delete alt of C to delete alt of null. Okay. Each call deletes the alternate node. Although it is recursive, it is referred to as tail recursive. So no extra stack space is used. And a tail recursion means a recursive function where a recursive call is the last operation. So no work is left after the call returns. Just for comparison, let's see the methods. Okay. We have time complexity and space complexity. This is the iterative method. And we have recursive method also. It gives big O of n, it gives big O of n, it gives big O of 1, and it gives big O of n. So there is no much of a difference. Both the methods are efficient. Iterative is preferred in interviews due to the simplicity and safety. So for this problem, the key idea is pointer manipulation. No extra memory is used and no values are touched. Once you understand the pointer movement, this becomes a very straightforward problem. Similar to the iterative approach, we first need to check the base case. If head is none or head dot next is none, return. That means if list is empty or has only one node, there are no alternate nodes to delete, so we simply return. The next step would be temp equals head dot next. The node right after the head is an alternate node, so we store it in a temporary variable. Then we do head dot next is equals to temp dot next. We simply delete the alternate node by skipping it. This directly connects the current node to the node after the alternate one. Then we clear the reference of the deleted node using temp is equals to none. So this helps with memory cleanup, especially in languages with manual memory management. Now we make a recursive call on the next valid node, that is self dot delete alternate head dot next. So this continues deleting the alternate nodes in the remaining list. Since this recursive call is the last statement, this is a tail recursive function. Now let's go ahead and run this against the test cases. As you can see, we are able to delete the alternate nodes. Thanks for watching.